Hi there, welcome back students to the fourth part or part 4 of my screencast on regression and correlation. The previous 3 screencasts, did quite a lot of work, or we explained regression in detail. And so this part number 4 starts explaining the background and the requirements of correlation as part of the entire set, which is on regression and correlation. So regression, I explained, was to see if there's a relationship between two variables, the independent and the dependent variable. And correlation again looks at the strength of the relation between the two variables. And so once we've established a regression line, so we've established that there's a relationship between I'm so sorry, between two variables. So there's a regression line between two variables. There are 3 measures of variation that we are going to use to check the strength of that relationship. And so the 3 measures of variation, the first one is known as the sum of squares total, or the total sum of squares, and this is a measure of the variation of the y observations and the mean of the y observations. That word should be and not are. The second variation is regression sum of squares variation, and this is a measure of the variation due to the relationship between the two variables. It's also known as explained variation or expected variation. We expect there to be variation when x varies, then y is going to vary to a degree, and that is known as the regression sum of squares variation. The error sum of squares is the unexplained variation. So this is similar, I'd say it's similar to normal standard deviation. You know that you expect, with regard to sampling, you expect a degree of variation in any case. If you're measuring the same thing, if you're measuring your weight, for example, 10 times, you get on the scale on and off 10 times, and your weight is maybe, say, 50 kilograms. You're going to sometimes find that it's 50.1 the first time, maybe 50.05, then maybe 50, then 50.1. So there's some unexplained variation, and that type of variation is the error sum of squares. It's due to factors other than the relationship between the two variables. So again, the relationship, the variation that we expect to see some variation because of the relationship, that is SSR, and the error variation is SSE, and the total variation is actually the sum of SSR and SSE. And so here I've written the sum of SSR and SSE provides a calculated or computed value for SST. And so this I've really got on for your background information. I'm not going to ask you to calculate SST, but this is the formula how to calculate SST. The most important for me, the very most important for me, is that you know this, which is SSR plus SSE is equal to SST. But for your information, because I think it is important to explain a little bit, this is how you obtain it. And so I'm also not going to go through this in great detail in the screencast, because this is in your notes, but this picture is an explanation, a description. Here's SSR, the formula for SSR, and a bit of an explanation on how to do that. And if you have time, then you can look that up in your textbook, or you can maybe even watch some Khan's Academy videos to find out how to calculate that. But that's not important for this course and for our exams. The same story applies with SSE. This is how you calculate that. A least squares regression selects a line with the lowest total of prediction errors, and that's the SSE. But I am going to, and I've also included this slide, which is what you need. I've called it an idiot's guide to calculating SST, SSR, and SSE. And so if you actually want to do it manually, this is how you do it manually, and I've written it out in Word format. But again, I'm not going to spend time doing this. I want to focus on the more practical, the applied parts of this course. What I'd like to focus on instead is two coefficients, and these are the two coefficients that help us to understand the correlation or the strength of the relationship between the two variables. The one uh, co- uh, coefficient is the coefficient of determination, and the other one is the correlation coefficient. But let me start with the coefficient of determination. By itself, the variation that we've just looked at, that I told you, I'm not going to pay too much attention to that because it's theory that we need to be able to apply the correlation coefficients, the coefficient of determination. Um, by itself, that information doesn't tell us very much, but we use that information to work out a ratio which is known as the coefficient of determination. And the coefficient of the coefficient of determination is a measurement or a gauge of the strength of the relationship. It's also represented by a R2, a R2 value. So let's have a look and see how we get this first coefficient, which is the coefficient of determination, R squared. R squared is actually obtained by saying SSR over SST. Now, I'll remind you that we said that SSR was the variation that we see as a result of the two variables, right? And SST was all the variation. So SST is SSR plus SSE. So if the variation or the movement that we've seen when we sample, and it's these two variables that we're sampling on, if the movement or the variation that we've seen is only due to the relationship of these two, then we understand that SSR would be a big number and SSE would be a small number. And so SST would obviously be made up of mostly SSR and there'd be very little or no SSE. And so if there's very little or no SSE, which is the error variation, then the coefficient of determination, or R squared, will be close to 1 or it will be 1. Now, R squared can range between either 0 or 1. But the higher the value, its value is, the closer it is to 1, it means that that model, that regression model, that line formula that we wrote out is accurate. So that's what it means. When your R squared is 1, then it means that there's little variation that you see in your sample, which is as a result of other things that is not the variation, anything other than the variation between the actual two variables that you are measuring. So it means that your SSR is very close or the same as your SST, because the same number over itself is equal to 1. If your SSE, or the error variation, is high, then this value will be less than 1 or significantly less than 1. And so a large R square value, or a large coefficient of determination, indicates that there's a very strong linear relationship between the two variables. And so how do we interpret that? If my R squared, or my coefficient of determination, is something like 0.850, okay? Remember, that has got to be between 0 and 1. So it can't be a negative value, and this also can't be greater than 1. But that means that 85%, and you see, you times that by 100 to give you that 85%, 85% of the total variation that we can see in Y as a result of X. Remember, there's variation that happens in Y because X has changed. So 85% of the variation that we see, the changes that we see happening in Y as a result of X, can be described or is because of the linear relationship between the two of them, which means that model is 85. When we say that model, the coefficient of determination for that model is 0.85. It means that 85% of the variation is because of the model. And only 15% is of the variation is unexplained. So we'll take 100, of course, and we'll subtract the 85, and that will give us the unexplained variation. And that is variation that you see in these two variables that you can't account for what happened that this variation is present. So that is the coefficient of determination. Now there's another coefficient, which is the correlation coefficient, and that we calculate by say simply it's r, and it's simply the square root of the coefficient of determination. So what we could say, one way is to say SSR over SST and take the square root of that. However, this tells us a little bit about the direction. Is it a positive relationship or is it a negative relationship? Because this R, or the correlation coefficient, takes the sign of your slope. So if R is +1, and 1 is obviously perfect correlation. Perfect correlation means the only variation that you see is variation because of the relationship, and that means SSR is also equal to SST, and that'll be 1. But if that 1 is a positive, it means the line that you have is a linear positive line. And if it's negative, then it means the line that you have is a linear negative line. And the correlation, this differs from industry to industry, and this I've actually seen with research projects on BTech level and master's level. Depending on the industry, it's very difficult for me to tell you what is good correlation and what is poor correlation. In general, in research, good correlation, which means this is a good model. If you do correlation and regression and you have this line, you develop the model using a sample. So you have a line equation to describe the relationship between two variables, but you want to find out, is this a good model or not? You're going to obviously determine what the correlation of determination is and the correlation coefficient is. Then that is going to tell you how strong that relationship is. For research purposes, they say it should always be more than 0.75, but I have seen in industry that people accept, sometimes they accept less than that. It depends from industry to industry. But generally 0.5 and less is weak correlation, and 0.8 or more is described as strong correlation. Yeah, and another way to calculate the correlation coefficient is actually using SSXY and SSX and SSY. But this we don't need to focus on for our exams. So earlier on, I mentioned the SST and SSR and SSE, and I explained that that is sort of variation, and I equated it, or I said it's comparable to standard deviation. But the true measure of standard deviation, or a truer measure of standard deviation, is the standard error of estimate. So that is the variation we see away from the line. And the standard error of estimate is something that we should also be, that is important to this course as well. So you need to understand what regression is, how to develop a model using data, how to interpret the model, make predictions of the model. Then you also need to be able to speak about the strength of the model. So for that, you need to know about the correlation coefficient and the coefficient of determination. And the final thing that we need to know about is the standard error of estimate. Now, the standard error of estimate is using the least squared method to find the line where the estimate is the least, using all of the data points. And so we have to calculate the standard error of estimate, which is the standard deviation around the prediction line, using the variable y and the variables of x. And the way that we calculate that is that SSE. Earlier on, I pointed out SSE, and I said that's the error from random sampling. So it's that standard that's going to give us the standard error of estimate. So SSE, to calculate the standard error of estimate, which is SSYX, we do the square root of SSE over n, which is the number of samples that is in that data set, minus 2. And the interpretation of a standard error of estimate is similar to that of standard deviation. Now I've come to the end. I've only got a few seconds left to just explain the assumptions of regression, and this is something that I could ask in the exam. This is a theory question in the exam, so please read through this and know that there are 4 assumptions of regression, which is linearity, independence of errors, normality of error, and equal variance. And so that brings us to the end of the screencast. We are on regression and correlation. Regression being the relationship, correlation being the strength of the relationship, and then also understanding the coefficients and standard error and SI.